I've got a decent video camera here because apparently my bandwidth causes Zoom to fuzz out sometimes. So I found that I've wasted a lot of time doing videos that people can't read because Zoom, and it's not, I don't think it's Zoom's fault, I think it's my provider. They're not giving me the service I pay for. Okay. There we have it. Okay, well now, again, our topic here is Gram-Schmidt. Gram-Schmidt orthonormalization process. So I want to go to Gram-Schmidt now. Knowing now that we can project one vector on another, you better capitalize that S. Okay, Gram-Schmidt. There's more to Gram-Schmidt orthonormalization process. Okay, one thing we can do. Again, we've got these vectors now. We have a vector v1, a vector v2. If we can calculate the projection, which we can easily do, and I'll calculate it for our vectors in a minute, but that's just a calculation. Okay? There's a process to be understood. So here's your projection onto v2 of the vector v1. And it's a vector, so we put an arrow over the projection, and naturally we've got two vectors here, and we put arrows over them. And it's easy to forget. If you don't have an arrow over this projection, it's the scalar projection, which is just the length of this, and positive or negative depending on whether this angle is acute or obtuse. Okay. In any case, once we have this projection, then notice that this vector here is orthogonal to v2. Okay. Now, what's that vector? Well, let's just draw us a vector diagram here, a little bigger maybe, so we can label it in case that becomes something we actually want to do. So we got this vector, and we've got this projection, and we've got a right angle. So this vector is v1. This vector is the projection, and it means all this. I'm not going to write out all those symbols, but when I write the final thing, I'll have those symbols. And this vector is orthogonal to v2. So we'll call this v1 perpendicular. That's not a standard notation, but for the purposes here, that means v1 component perpendicular to v2. We can calculate the projection. So we can calculate v1 perpendicular. Why? Because this vector plus this vector equals this vector, equals v1. The projection plus this v1 perpendicular equals v1. So we can write projection, which is shorthand for projection on v2 of v1. And let's go ahead and write it out now. On v2 of v1 plus the vector I designate as V1 perpendicular, or I denote as V1 perpendicular, equals V1. Well, if that's the case, how do we calculate V1 perpendicular? We know V1. We can easily calculate the projection of V2 on V1. Well, let's just do some algebra. Let's subtract this from both sides, so that V1 perpendicular equals V1 minus this projection. That's it. So now we have two perpendicular vectors. Okay? So I'm going to say the set V1 perpendicular, V2 is a basis of R2. We know it's a basis because they're two vectors in a two-dimensional space, and they're certainly not linearly dependent, because that means in R2 they'd be multiples of each other. And this is perpendicular to this. Okay? And we're assuming they're non-zero. They have to be non-zero because remember V1, V2 was originally a basis. Since V1 and V2 formed a basis, we know that those vectors aren't parallel. Okay, so it's now a basis of R2. Not only that, this is an orthogonal basis, which you know from your study of basis makes things particularly simple. Okay, so it's a basis, it's an orthogonal basis, and often we want an orthonormal basis. Okay, well, if we want an orthonormal basis, we just go ahead and divide both these vectors by their magnitudes, and it's orthonormal. Orthonormal means orthogonal and unit vectors. So we have a basis of orthogonal unit vectors. So we say that's an orthonormal basis. For the Zoom recording, some of this might be obscured, might not, by the watermark, but there we have it. Okay? Now, there's one modification to the process I gave you for finding the orthonormal basis. If we know we're looking for an orthonormal basis, even if we aren't, it really helps if we first normalize V2. So what we would want to do is, and I'm just going to picture it, just makes a calculation a little simpler, and you know we're going to have to normalize V2 anyhow, divide it by its magnitude, make it into a unit vector. So we got V1, that's V1, and V2, if we use V2 V2, not V squared. Now this red chalk erases badly, so I'm going to have to use drastic measures here, which means I have a slightly damp board. Okay, this vector here is V2 over the magnitude of V2. Well, that simplifies calculation of the projection. So we can easily show that. And let's call that V2 norm. Okay, call that normalized V2. Now you know when you see it in your book, you're going to use different letters once you normalize things. I'm pretty sure that's the way your text does it. Hadn't really looked at it. V2 normal is normalized. Okay, so now your projection onto V2 norm of V1 equals didn't leave myself room, just V1 dot the normalized V2 multiplied by the normalized V2. Okay, you don't have to divide by magnitude of V2 here or V2 norm here. You don't have to divide by magnitude of V2 norm here, because the magnitude of V2 norm is 1. So it simplifies the calculation if you first normalize V2. So that's the way we're going to approach it when we go to higher dimensions. If we had 3 vectors, V1, V2, V3, that form a basis for R3, or any three-dimensional space, with an inner product. If you've got an inner product, you can always do this. Then you can just start with 2 of the vectors. Okay? Normalize the second one, and then subtract the projection from the original vector to get the vector that's normal to V2. And if you first normalize that, calculation's simpler. You're going to have to normalize it anyway, you might as well. Okay, well, then you go to V3. Now what are you going to do with V3? Well, you're going to subtract the projection of V3 onto V1 and onto V2 and so forth. Okay, we're going to do that, but let's just do a quick example. The example that we started with.